Okay, in this video we're going to be looking at reaction profile diagrams. So we've already looked at exo and endothermic reactions, and we've described them in terms of the energy they are giving to the surroundings in the case of an exothermic reaction, and the energy being taken in from the surroundings in terms of an endothermic reaction. So the first thing here is a quick start activity. I think burning a match is because, okay, so again, you can be completing that yourself. You don't even need to be going through that, but things to consider are when you burn a match, what evidence is there for it being exo or endothermic? And think about that particularly in terms of the energy transfers. Is it taking energy in? Is it giving energy out? What kind of temperature change would you expect in that reaction? So one of the things we need to consider, as well as the energy change of the reaction and the energy of the reactions and the energy of the products, is also the activation energy. Okay, so the activation energy is defined as the minimum amount of energy particles need in order to react. Okay, so not all reactions just spontaneously occur. The reactants need to have enough energy in order to react in the first place. Okay, and that's something that we're going to incorporate into our reaction profile diagrams. So this is a sort of generic reaction profile diagram. You tend to have energy on the y-axis and progress of the reaction on the x-axis. Sometimes it will say something like reaction coordinate, but it's the same thing. What they're really saying is start and end of the reaction. So we should know that at the beginning of the reaction we have reactants. So on the left we're going to have our reactants, and at the end we have our products. So on the right we're going to have our products. So you'll notice there's no actual values on either of the axes. There very rarely is, because we're not actually interested in the value at this point. We just want to see the energy of the products compared to the energy of the reactants. So for both of these, we've got an exothermic reaction and an endothermic reaction. Now, if it's exothermic, then we're going to expect to see our products at a lower energy than our reactants. But if it's endothermic, we're going to see them at a higher energy than our reactants. So it makes sense to put your reactants more or less in the middle of that y-axis. Because if you put them too high, you don't give yourself enough room. If you potentially have to put them above, and if you put it too low, again, you're going to cause yourself issues with room. So if you're drawing it freehand and they've given you one that they want you to complete, start with your reactants pretty much in the middle. So we're going to label that line. So this is the energy of our reactants. And as I just said, in an exothermic reaction, the products are a lower energy than the reactants. Okay, so I'm going to draw a line that's lower energy than our reactants, and that's going to be my products there. And in an endothermic reaction, we have our products having more energy than the reactants. So I'm going to draw my line higher than the reactants. Okay, now the one thing you want to make sure you do, and this is something they're not going to do for you in the exam, is make sure that these lines overlap. Okay, so I've made sure I've drawn them long enough that they overlap each other. If they don't in the exam, then just extend them yourself so that they do overlap. So the things that we can see, we have obviously a difference in energy between the reactants and products. So the energy change between the reactants and products here is negative, isn't it? It's going down. So that's energy that's being released to the environment, into the surroundings, which we'd expect because it's exothermic. Here, we've got a positive change in energy. The products are higher energy than reactions. Where did they get that energy from? Well, they took it in from the surroundings, okay, which is again indicative of an endothermic reaction. So the things they're going to want you to do, they're going to want you to be able to place your product in the correct place. So if they are giving you some information that tells you that this reaction is exothermic, they're expecting to see the product at a lower energy level than the reactant. If they've given you some information that shows the product being higher energy, the reaction being endothermic, then they're expecting to see the product at a higher energy. So the first thing we can label is the energy change. Okay, now I'm pretty pedantic about this, so make sure you get your ruler. Here's one that I got out of a cracker. So you're going to draw a line, a vertical line between the reactants and products. So this is why you wanted them to overlap, so that you can have a perfectly straight vertical line between the reactants and products. I'm going to do the same over here. Vertical line between the reactants and products. And the direction of this line is important, okay? And every single reaction you've ever written or seen will go from reactants to products. So this is no different. It goes from reactants to the products. Over here, it goes from the reactants to the products. So in this case, in our exothermic reaction, it's going down. The energy is going down. So this is going to be a negative change in energy. This triangle here is delta. It means change. So we're going to have a negative change in energy. Here, it's going up. So we have a positive change in energy. So exothermic reactions have a negative change in energy because they're giving that energy to the surroundings. Whereas we have here our endothermic reaction, which is taking in energy from the surroundings. The other thing that we can label on here is the activation energy. And to start with, all you have to do is draw a loop from the reactants to the products. And it's the same over here. A loop going from the reactants to the products. Now, in order to label that, all you're going to draw is a line, again, a vertical line. Get your ruler back out. Okay, a vertical line that goes from the reactants to the top of that loop. This is your activation energy. And again, over here, from reactants to the top of that curve. Remember, it's your reactants that need that energy, not your products. Your reactants need this energy to react. So it's always going from reactants to the top of that curve. So there is our activation energy. And that's it, okay? All they're ever going to ask you to label is the products in relation to the reactants, the energy change, and the activation energy. And again, just use your ruler, make sure they're vertical arrows, vertical lines, and make sure the arrows are going the correct direction. So, describe how you can tell from the reaction profile diagram if the reaction is exo or endothermic. Well, simply, if the products have a lower energy than the reactants, then the reaction is exothermic. And vice versa. So if the products are higher in energy than the reactants, then the reaction would be endothermic. But for all of these, you're always doing reactants, products in the correct place, higher or lower, depending on whether it's exo or endothermic, labeling the energy change, going from reactants to products, vertical line, and then activation energy, going from reactants to the top of that curve. So if we turn the page, we've got some examples of some reactions here. Now, I'm going to do the first two, and then I'll leave it for you to do the last two. So the first thing we should note is that this is a negative energy change. So straight away, we should be able to identify this is exothermic. So we're going to draw our reactants. And again, we're going to go straight down the middle for that. And because it's exothermic, our products are going to be lower in energy. So we're going to draw our second line there, okay? Lower in energy. And we have a bit more information. We don't just know reactants and products. We know what the reactants are and we know what the products are. So we can actually label these lines properly using the balanced equation. So our reactants are 2mg plus O2. And our product is 2mgO. We can label our energy change, and that is going to be a vertical line going from reactants to products. And again, we don't have to just say energy change, we know the value. Okay, our energy change is minus 1250 kilojoules. And finally, our activation energy and we're going to draw a vertical line going up from the reactants to the top of that, and there is our activation energy. So I'm going to leave this second one. You can do this second one. I'm going to have a look at this third one here, okay, the calcium carbonate. Now we should see from the energy change that it is endothermic because it's positive. So, same again, we're going to draw our reactants about halfway up. This time, because it's endothermic, I'm going to draw the products at a higher energy level. We're going to label it, so our reactants are CaCO3 and our products are CaO and CO2, so calcium oxide and carbon dioxide. We're going to label our energy change, vertical arrow again, going from reactants to the products. We know the actual value of that, it's positive 785 kilojoules. Because it's endothermic, it's taking in 785 kilojoules of energy. And then our activation energy, okay, it's going to be a loop like that going from reactants to products. And we're just going to label the line between the reactants and the top of that curve. There we go. And we're going to label that activation energy. All right, so there's one here for you to have a go at, and there's one here at the bottom that you should have a go at. And another thing that I want you to think about is the effect that you would expect if you add a catalyst. Okay, so you might want to look this up because again we haven't done topic 6 yet. We haven't done rates of reaction, we haven't covered catalysts, but if you look it up very quickly in your revision guides or online, just find out how a catalyst speeds up the rate of reaction, and I think you'll find it's quite simple. You'll be able to see the effect it's going to have on our reaction profile diagram. Okay, so if you could just finish off these last two and then just have a look up at how do catalysts affect rate of reaction. So how do they actually work? What do they do to a reaction that allows it to change its rate? Okay.